All right, now, in the last video, we just looked at a word problem that we did at the start of class to get the idea that with systems of equations, we have two equations, and we're looking to try to find basically the point of intersection. That's what you do most of the time with systems of equations. Okay, so I'm going to take another example. We don't know what the context is, but I'm taking two equations that are linear. You've seen these on your test, each one individually. And what we're going to look at, I'm going to have you graph these two lines on the same coordinate plane. Okay. And then we're going to use that graph to solve the system of equations. So this right here, these two equations make a system of linear equations. And so we're going to graph to start with, solve the system of linear equations by graphing is what I'm going to do. Okay. So the idea is I'm going to graph the two equations and I'm going to see if I can tell what the point of intersection would be. All right, let me see if I can get the backdrop that looks like graph paper. That always shows up. Nah, I'm not going to try. Okay, so what we're going to need to do is take each equation and get some ordered pairs to satisfy the equation. So I'm going to do this one in red, and I'm going to do this one in blue. Okay, let me make that a little skinnier. Okay. All right, so first thing I'm going to do is look for some ordered pairs that I know satisfy that equation. And then I'll do the same for the other one, and I'll get those two graphed. Okay, so let me go ahead and put a coordinate plane over here. And I'll wait to put my scale on it until after I get some ordered pairs. All right, so it is up to you to pick what you want in order to find the ordered pairs. And really, you can pick anything that you want and then try to work it out. Okay, so if I put in, for instance, a 0 in the x spot, then that would mean I'd have 2 times 0 minus y equaling 5. So that would be that negative y equals 5. So I'd have to divide by negative 1. Let me do that in black. I'd have to divide by negative 1 on both sides to get the y by itself, and the y would turn out to be 5. So when x equals 0, then y is 5. So that goes together to make an ordered pair, and I'll come over here and I'll plot that ordered pair in just a minute. And by the way, that's a special point, isn't it? That's an intercept. So I might find what happens when I plug in 0 for y. Okay, so I'm going to go back to that equation, 2x minus y equals 5. I'm going to put a 0 in the y spot. Then that means I have 2x equaling 5. And so x would wind up being that fraction, 5 halves. So yes, it's 5 halves, but I'm going to graph that. So it's really good to know it's the same as 2.5 or 2.5. Okay. And that's going to be an ordered pair that I'm going to go and plot. All right. And then you might find, another ordered pair. For instance, if I plug a 3 in for x. Okay. Then, and see, a lot of people hesitate. Well, what should I plug in? You can plug in anything you want and just work out what the other coordinate should be. So I could plug in a 3 for the x. That's 6 minus y equals 5. I might be able to, on that one, just see, can you see how y would have to be 1? If not, you'd continue solving and you'd subtract 6. So you'd have negative y equals negative 1, and then divide by negative 1. And so y would be 1. Okay. All right. And so here we have 3 points. I'm doing these in red over here. Let me get the scale on there. So let me just go out. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. I'm trying to do this carefully. 5, 6, 6. I'm going to try to read what the answer is off of the graph. So I want my tick marks to be equally spaced. I want to be careful when I plot my points. 1, 2, 3, 4, 5, 6, 7. Okay. All right. So here we have 1, 2, 3, 4, 5. 0, 5. Now 5 halves 0, that's 2.5, 0. So I'd come out here to 2.5, 0. And then the 0.31 would be 3, 1. Uh-oh. Something's wrong. Do you see that? I made a mistake somewhere. That's why you find 3 points. Somewhere there's a mistake. They have to all line up. So I got to go back and check my work. Okay. And so let me go back and look. So when I plugged in the 0 for x, I had negative y equals 5. I divided by negative 1. Oops, right there. Should have been a negative 5, shouldn't it? See how the 3 points didn't line up? That's how I'm going to catch that. And when I plot my points, I'm going to this one, and it's really supposed to have been down here. Okay, that looks better. So that's the 2x minus 5y equals 5. So let me get that one on here. Draw it nice and long. And remember, that's y equals, that's not y equals. I didn't do it in y equals. That's 2x minus y equals 5. Okay, so that was one way to graph it, just to use it as is and just to find ordered pairs that satisfy it. Okay, so let's do the same on the other one. So I'm going to look for ordered pairs that satisfy this. Okay, so I could go in and let me try plugging in a 0 for x. I really like that point because that's the y-intercept. If I plug a 0 in for x, I'd have 3 times 0 plus 2y equals 4. That works pretty good because I can see 2 times 2 would equal 4. You know, I know that y has to be 2. So there's an ordered pair on that line, the 0.02. Okay. I don't like this one so much. If I plug a 0 in for the y, that winds up being 3x plus 2 times 0 equaling 4. So 3x equals 4. And if you divide by 3, you wind up getting 4/3 for the x. Okay. If you change that into a mixed number, don't forget that's that's not 1 point. That's 1 and a third, 1 and a third, or 1.33 keeps going if you change it to a decimal. I didn't like that one so much because of the fraction, but I can still use it to check whether my points are okay or not. All right, let's see. What if I put a 2 in for x? See how that one works out. If I put a 2 where x is, I need to find out what y would need to be. So that would be 6 plus 2y equals 4. So I know how to solve that. I'm just going to subtract 6. That's going to give me 2y equaling negative 2. And when you divide by 2, we'll find out that y is equal to negative 1. So when I plugged in a 2 for x, the y was negative 1. So that gives me another ordered pair, 2, negative 1. All right, so let's plot 2, negative 1. That would be like right here. And then 4 1/3, that would be 4/3, 0. That would be 1 1/3. So that would be about right there. Okay, those are looking like they're lining up. So I'm pretty sure I got those done correctly. There would be that line. Okay, and that line was 3x plus 2y equal 4. Now don't worry, you don't have to solve equations by graphing, or you don't typically choose to solve a system of linear equations by graphing. It's just starting with a graph helps you kind of understand what it really is you're looking for. But we normally solve them, and you need to learn how to solve them using algebraic techniques, and I'm going to show you that also. Okay, so when it says to solve the system by graphing, when it says that, solve the system by graphing, what they're really wanting you to do is graph them and then look for the point of intersection. Okay, you're not going to always be able to identify that easily from a graph, especially if you do it by hand like I did. This one appears, this point of intersection right here appears to be 2, -1. It looks like it's 2, -1. I know 2, -1 is on the first equation, but let me see if 2, -1 would have been on the second equation. So let me check this before I tell you that this is the solution to the system. Let me check and make sure it really works. If I put a 2 and a -1 in, does it satisfy that equation? 2 times 2 minus -1, does that equal 5? That'd be 4 plus 1, sure would. So that would have been a point, I just didn't use it, but it would have been a point on the other line as well. So when you're solving a system, you're looking for a point of intersection, point that is in common to both lines. That right there is the solution to this system. So the solution is the ordered pair 2, -1, that point that's in common. Okay, the point of intersection. All right, so we definitely don't want to have to graph every system in order to find the intersection points. You can't identify the intersection point from a graph in a lot of cases. Like if the ordered pair turned out to be, 3/7 and then 5, you couldn't determine the 3/7 from the graph. You need an algebraic approach. Okay, so make sure that you're also focusing on these algebraic approaches. All right, so let's look at how we could solve the system of linear equations rather than graphing by using an algebraic technique, okay? So let me put it in so here, the directions here are going to be to solve the system using, and I'm going to use 2 words. Some books call it elimination. I know a lot of you use other videos. You might also see it called the addition method. Okay. So solve the system of equations using addition or elimination. And they might say the addition or elimination method. Okay, so here's the idea. So you're going to start out sometimes with these 2 equations. So here we have 1, 2x minus y equals 5. Here's 1, 3x plus 2y equals 4. And this is some system of equations. We're trying to find the point of intersection. And we assume that we haven't already graphed it. And we don't know what the answer is ahead of time. But we're looking for it. And we want to use an algebraic technique. Okay? In the back of your mind, though, I want you to think, this isn't necessarily how those equations looked, but I'm looking for this point right here. So I have these 2 equations, equation 1 and equation 2, and I want that point that's in common to equation 1 and equation 2, okay? So here's the logic of, this is the addition or elimination method. Here's the logic of it. I'm going to wind up adjusting the equations so that when I add them together, one of the variables will cancel out, okay? And so when I'm looking at this one, you can always get either variable to cancel out. But when I'm looking at this one, I'm noticing that in front of the y, the coefficient is 2, positive 2. In front of the x, I have an understood -1, okay? So what I think would work really well would be if I would just take that first equation and modify it in a way that would be okay. I'm going to take that first equation, this whole thing, I'm going to multiply through by 2. Because it's an equation, it's going to be okay to do that. Because I can do 2 times the left side as long as I do 2 times the right side. I won't really have changed the problem. It'll look different, but it won't really be different. So that's what I'm going to do. So imagine that 2. I'm going to multiply it on both sides. So I'm going to distribute it here and also multiply the 5 by 2. So that top equation becomes 4x minus 2y equals 10. Now that, what I just did, wouldn't have changed equation 1 at all. It would still be right here. Still that same set of ordered pairs. I haven't changed it at all. All right, so what I'm going to do is bring this other equation over. And if you're using the addition or the elimination method, one of your goals is to get these numbers to be opposites. And the reason you want them to be opposites is a negative 2y and a positive 2y would add up to be 0. So what we're going to do now is we're going to add these two equations together, and notice they're already lined up where the like terms are lined up. Okay, so when I add 4x and 3x, I'd get 7x. The negative 2y and the positive 2y, I made it so those would cancel out. Don't lose track of your equal sign, and then add what you have on the right-hand side. So I know that 7x would have to equal 14. Okay, so this is a new equation, different from the others. If I finish solving that, see how it's only got one variable. So I've turned it into a chapter 2 problem, and I'm able to just solve that by dividing by 7, and I wind up with x equaling 2. And x equaling 2, that is a new equation. Okay, x equaling 2, though, would be related to these others. It would just be the vertical line going right there through that point of intersection. Okay. So what we found so far is that the x-coordinate of that point of intersection has to be a 2. All right, now that's basically the main part of the elimination method, but you're not through with the whole problem. So now what you're going to do is you got to find the y-coordinate, don't you? So for that, you're going to take either one of the equations. Doesn't matter which one. A lot of times I'll just take the one right at the bottom, and you're going to substitute 2 in for the x. See, you know that point is a point on each equation. So it doesn't matter which equation you take. So I'm just going to go and pull 3x plus 2y equals 4. I liked it because it was all positives. And then in place of this x right here, I'm going to put a 2. And then I have an equation in one variable. We did this in chapter 2, and I'm going to solve that equation in one variable. So that means I got to get the y by itself. So I take away the 6. I'm left with 2y equaling negative 2. And then I'm going to divide by the 2. And I wind up with y equaling negative 1. So remember, that was when I plugged in the 2. So when x equaled 2, the y turned out equaling negative 1. So what I'm going to do is put those two together and make that ordered pair. So y equal negative 1, So y equals negative 1, going back to that graph, okay, is actually the horizontal line through that point of intersection. This is the horizontal line. This one was the vertical line through that point of intersection, but I know all the y's have to be negative 1 on that. So that y coordinate right there turns out to be negative 1. Now you're supposed to, of course, remember that we haven't just solved this by graphing. So we didn't know that the ordered pair was 2, negative 1. I didn't see the graph. I'm just kind of using that sketch as an image for you to think through the process. So if you're going to use elimination or addition, this is what I have to see right here. I have to see where you worked to try to get either the y variables to have opposites out in front or the x's to have opposites out in front. So when you add the two equations, see how the variable went away? It was eliminated. So you used addition, see we're adding the two equations to eliminate one of the variables, because if you have an equation in one variable, you know everything there is to know about how to solve that. So then you take the x equal 2 and the y equal negative 1, and those aren't your individual answers. You put them together with the x first and the y second, and that is the solution to the system. And we just found it using a process called elimination. Okay? All right, so we're going to work on trying to solve things using elimination. But we're also going to work on trying to solve systems using another algebraic technique that works well in some cases, and you'll need it at times as well. So that's the main focus of your job, is going to be being able to do the algebraic solution process. So you want to work really hard on solving by elimination, and then I'm also going to teach you how to solve by substitution. If you learn nothing else, those are the two things I want you to be able to do. Okay. All right, so let me pull up the packet again, kind of show you where we are in this packet. So let me see, I'm trying to move down. All right, so we were working on just showing you how to graph the system to find the solution. So we did that, and then we did it algebraically. Now I want to look at this page right here with you. Okay, so this is kind of like a summary of what could happen. So we just saw how I graphed the two lines a second ago and they turned out to intersect. Okay, so that would be a description of the graph. So the lines could intersect like that first case. Okay, let me see if I can move this up just a little bit. We can make it a little smaller. I'm gonna, because I can't write on my PDF, so I'm gonna snip this so I can write on it. I want you to add a little bit to that notes page. So I gave you a packet in class because I really want you to write some notes to yourself on these. All right, so this is the situation we just had. This was the movie problem and the last problem. We had a situation where the two lines intersect. Those are called intersecting lines, okay? Sometimes your two lines are going to be parallel. So that's what you call the graph. They're parallel lines. And sometimes they're the same line. A more formal word is that they're coinciding, but it's like one line and the other line, they're right on top of one another. So those are like the three situations. Now, of course, they could be in any orientation. So I'm not saying they always are in that, like the coinciding lines could be like this. They don't have to always be falling. All right. Now, we already know that to be parallel, you need to have the same m's and different y-intercepts. Same slope, different y-intercepts. Well, to be the same line or coinciding lines, you'd have to have the same exact M and the same exact B. If you did, you really only have one line. And then to intersect, they just need to not be parallel. The lines would need to have different M's. And that would, if the slopes are different, then they're going to intersect somewhere. This is the usual situation most of the time. And then your job is to find that point of intersection. All right, occasionally you hear special words used, so I just want to mention it. With parallel lines, we sometimes call the system of equations inconsistent. That means that it doesn't have a solution. That's what that means. And if the lines are coinciding, it's like they can't move separate from one another. They're stuck together everywhere. A word you hear used there is that the equations are dependent. So if you ever see them talking dependent, it means you have one line. If you ever hear them using the term inconsistent, it means your lines are parallel. And see, they never intersect, okay? All right, so what the earlier things I did were supposed to give you a feel for is that usually we have two lines and our job is to find that point of intersection. That's because the solution to a system of equations is going to be any point or points of intersection that we have. So it's a point that satisfies both equations. So it's an ordered pair that you could plug into both equations and it would work. All right, so notice if the lines are intersecting, you're going to have exactly one point of intersection. If the lines are parallel, there's no points of intersection. They never intersect. And see, if they're coinciding, one line's on top of the other, there's infinitely many of them, okay? There's a whole bunch of them. Every single point on the line is common to the other line. All right, and then one last thing I wanted you to think about is if you're actually asked to find the solution, then your job is to actually give me that ordered pair with some x and some y in it. Like the point 2, -1, for example. If they're parallel, they don't intersect. So if you were asked to solve, you would just say there's no solution. And then if the lines turn out to be really the same line and they ask you to solve, to me, you should say something like this, that the solution would be all points on the line. This is a formal way of saying that. It's a formal way of saying the solution would be the set of all ordered pairs such that they satisfy whatever the equation is. You would put that right here, okay? Now, what my math lab says a lot of times is just that there are infinitely many solutions. Okay, so I'll let you say that, but to me, it's not quite as good because this over here is not a solution. It's not on the line. This isn't a solution. It's not on the line. So I like all points on the line. There are infinitely many solutions, all the points on this line. Okay, but that guy's not. This guy's not. Okay. All right, so the idea you're going to have is you're going to have a system of equations, and they might be parallel, coinciding, but you kind of assume they're this one, and you use an algebraic process to try to find that point of intersection. Okay, so that's where we're going in the next video.